of experimental math. The first talk today for 48 minutes is by joint with Elaine Wang and Christoph. And then we have 12-minute break, and then we have the second talk by Professor Shaoxi Chen from 5 to 5:48. Then we have a break, and everybody is welcome to come at 6:45 to Japanese restaurants. And right after Shaoxi's talks, let me know whether you can come. Thank you.
Hi everyone, my name is Elaine Wang. This is a joint talk with my advisor, Christoph Kuchan. We are associated with the Austrian Academy of Sciences, and these are two associations. This is Radon Institute of Computational Applied Mathematics and the Enumerative Algorithms and Enumerative Combinatorics Group in Austria. And this work is actually the work of Christoph and his collaborator Totsupon Ik Tanatupananda, and that who used to be Doran's student. I think he graduated in 2008. And I am joining this project and have been asked to sort of give the introductory part just to prepare you for the wonderful results that they had produced for this paper. And so at that moment I will pass the baton to Christoph to explain what the results are. And so yes, and so I've learned that in the past few months, I started in February, and in the past few months I have learned that doing mathematical research sometimes involves picking up scraps of other people's work first. They do all the nice work, and then you have little problems that you try to solve. And hopefully one day, by solving these small problems, you will learn enough to solve your own problems. And so my goal here is to pick up their scraps and continue some of the leftover work from this work, and yeah, and hope to learn something from that. Okay, so that's my background. Okay, so let's just start with the problem itself. And so we start off with a paper from 1979 by George Andrews. This paper introduced us to a very special determinant that counts descending plane partitions. And I would, assuming that you all know what a descending plane partition is, but just to have something in mind so that we can remember what it is. And I use this example to remind myself of what it is, to help me remember what it is every time. It should be a 4, I think. Okay, so it's just an array of numbers where it's every row decreases in size, and every term in each row is weakly decreasing, and every number in each column will be strictly decreasing. And furthermore, I think the leading number in each row must be smaller, must not increase in this case. Okay. So for this determinant looks a little bit funny, because here you have an array of numbers that have specific properties, and yet you have this funny determinant with binomial coefficients and some Kronecker delta. And furthermore, you also have this interesting parameter here, where we represent it as lambda, but lambda is actually mu minus 2, and mu here is indeterminate. And so it's a bit funny looking, and you wonder, okay, so how does that relate to that? Okay, so. And we're going to explain what Andrews did, and then we're going to try to explain the relationship.
Why do you need a mu? Why can you stick to lambda?
I think this is for, I think Andrews had used the mu.
Oh, mu is something that came out from combinatorics.
Exactly. And so,
but instead of writing mu minus 2, it's more convenient to write lambda.
Exactly, that's right.
It's just our laziness that we realized after we had written the paper that this lambda is better, and we were too lazy to change everything in the whole paper. That's why we both.
Yes.
It's a good reason.
That's a good reason. And for reasons that will be clear later, we will denote this particular determinant as D with subscript 0 and 0. And so I want you to notice first that we start here at 1, the index at 1. Andrews actually started at 0, 0, and we manipulated a little bit to start everything at 1. So all of our determinants in this paper will start at 1, actually. So the 0, 0 is actually referring to Andrews' original formulation of the determinant, which started at 0. Okay. But we'll just denote this determinant as 0, 0. So let's see, let's just review the result that Andrews gave in 1979. He was able to find a nice formula for this D00 closed form in this form, where these R's is a product of these R's. And what are these R's? They are basically rational combinations of these Pochhammer symbols. And so you can view them as a fraction of the D's if you want to. But it's in the end, what you should notice is that it is reasonably nice looking. Okay, and notice that there are no more deltas. The mu appears again, unfortunately. Sorry about that. But this is how he had used mu in his paper, and all of his formulas had mu. Yes, and just a quick reminder of what the Pochhammer symbol is. Okay, so this was the nice closed form that he derived in 1979. Okay, and then furthermore, a year later, he said, you know what, that's not interesting enough. Let's maybe take a look at a slightly different determinant. And if you notice up here, he actually called this interesting. This determinant actually looks interesting. And he computed a few of the terms, and he says, okay, well, it looks nice, and maybe we can formulate some sort of a pattern, just like we did before with the D00 determinant. And so just to compare, I just want to show you really quickly what the difference is. Maybe it's not so obvious here because we started at 1, but when he started at 0, I think this was a J. And so what he did was he said, hey, let's do, and the J and the I are interchangeable here. So let's add 1 to the binomial function. Let's see what happens. Okay. So what did he conjecture? In 1980, this determinant, with the slightly altered determinant with a slightly different binomial coefficient, had looked like this, and he was able to conjecture the following formula. I want you to notice that if we call that D11, I want you to notice that the conjecture only involves even ends in the numerator and then the odd ones in the denominator. So this is a conjecture of a rational relationship between the D's, but only at the evens in the numerator and odds of the denominator. Okay. And so it looks, again, it's a lot of Pochhammer symbols. Okay. And you can actually hand simplify this expression to make it look just a little bit nicer. And so, and this is just a conjecture. And in 2013, Christoph and Ake actually used computer algebra and a variant of Doran's Holey ansatz to prove.
So it was open on his heels?
Yeah, exactly.
No, it appears as a problem in his second determinant paper.
That's right. Problem.
That was problem 34.
Yeah. Yes. So this was proven in 2013. So we have a nice formula for this. Now you might be wondering, well, do we have a nice formula for D11? Not the ratio, but D11 itself. And spoiler alert, the answer is yes. Yeah, and this will be shown in a few bits. So you might be wondering, how can such a determinant look so nice? And so if you attempt to calculate these determinants for the first 10 examples, it looks a little bit intimidating at first. But maybe we can see some pattern. Are there any possible similar factors that you can see? In which of the D's do we have some similar factors here? Let's see. So we have this ugly cubic here in the terms of mu gets repeated right there. Yes. And observe that that's when n equals 6 and 5. So we have that relationship between the two, the even and the odd in this case. and you can see the pattern being repeated every pair thereafter. Yes. Right.
So ugly over ugly is nice.
Yes, ugly over ugly is nice. That is a very nice way of putting it.
It's the same ugly.
Yes, exactly. Okay, and so now we understand why this formula, could be so nice. Oh, what happened? Oh, it showed the reference already. Yeah. Is there a way to go forward really quickly? How did I do that? Oh, sorry.
Control.
Yeah. Okay, sorry about that. It's my fault. I must have accidentally asked something. Oh, yes. Okay. Pardon me, give me about 15 seconds here to reorient myself again.
No.
No, I have to do my sorry. Okay, this requires a little bit of...
This one?
This one right here, yes.
You don't have it, time is out. Doesn't count.
I know.
Okay.
So did I get 15 seconds off for that? Okay, thank you.
Hang on.
Yes, thank you. Okay, okay, so great. Okay, so what is now that we have these determinants and we have some feeling for how they look, and we know that it's related to Pochhammer symbols, we know that they have nice ratios, what can we do? Can we make it more general? Can we make it more, even more interesting? And the answer is sure. What if instead of starting the indices at 1 and 1, what if we slightly adjust its corner? Instead of at 1, 1, you start at ST, for example. And use the same Kronecker delta and use similar binomial coefficients. And would that be also nice? And that is the question that we address here, or that Aiken Christoph had addressed. And so at first you think, okay, well, maybe I can handle this, but I really, really don't like the Kronecker delta. This is also really awkward to start at S and T. I'm more comfortable starting 1, 1. So maybe the first thing you do is to do a quick change of variables and try to manipulate this so it starts nicely. Do a little, this got more complicated. The binomial coefficient looks pretty complicated there. I don't know if we like that too much. Maybe we can work with this determinant instead and see what happens. And so if you consider what we have done so far, or what Andrews has done so far, now the 0, 0, it has more meaning because now we say, oh, we're considering S and T starting at different positions. So in Andrews' case, he started at 0, 0 for that determinant. And also in Andrews' case, he also had the 1, 1. He considered the 1, 1, we're starting at 1, 1 as well. But he was not able to get the closed form for the 1, 1 because, and that left the room open for a paper by Christoph and Nate to be able to do it. So these are some of the special cases, right? So we want to study it in general.
Only conjectured it.
Yeah, Andrews conjectured it.
And Christoph and Nate proved it.
That's correct.
And the monstrous conjecture was proven or conjectured? Or both?
Christoph and Nate in 2013 conjectured the formula.
But at the time did not prove it.
That is correct, yes, because it was proven in 2018. Yes. Okay, okay, so now we want to figure out, okay, now that we have a sort of a generalized version of Andrews' determinant, can we interpret it, can we calculate it, can we find formulas for it, etc. Okay, so this is the object of consideration now. Okay, so to make things a little bit easier, we try to not write the binomial coefficient binomial coefficient in this way. So we substituted with this little b, which you can see depends on I, J, S, and T with some indeterminate lambda. Okay, and so now we make it look a little bit cleaner, and furthermore, we can make it look even more clean by just applying Laplace expansion as you normally would for a determinant. And you can see that you have the sign and you have the minors of the corresponding matrix. Okay? Now, this is still not that nice because you still have this Kronecker delta. And so if you want to, it just so happens that when you apply if you do a little bit of simplification, this actually can be factored out. Okay. and you get this term that gets taken out of the original Laplace extension. Yes. And so now you think, okay, well, this is better. At least we don't have to deal with this. We have a finite sum here. Maybe this is more doable, and we can deal with this. Okay. And so let's see. And keep in mind, by the way, we are doing Laplace expansion only along the ith row, and so, or ith column. And so if we continue to do, if we want to evaluate the minors, we have to continue to do the Laplace expansion. And so we can do this recursively. Okay. And therefore, finally, in the end, we get this. And you might think, okay, well, at least all the Kronecker deltas are removed, and now we have somewhat of a nice formula for the determinant, provided that we can actually figure out what this means here, okay? And so I just want to do a quick reminder. So the B here, I actually are these binomial constants here in the matrix. Okay, so that B here comes from the matrix that is obtained when you delete this many rows and this many columns. From the matrix. So we want to sum up over all of the possibilities, all of the possible combinations of this. Okay. Okay. I'm going to pause here for a second so that I can look at the time and also maybe see if the audience has any questions about what we are doing so far. Yes.
Well, it looks more complicated than the original one. There was a single determinant, and I have a huge sum, alternate sum.
Yeah, it does. But at least the Kronecker delta is gone.
Well, no offense.
No,
Kronecker delta is more
nice.
More appealing than this huge sum.
Yes. However, you can see that if we are able to provide maybe perhaps an interpretation of this particular matrix, maybe we can do something like that. Okay, so now we want to switch gears a little bit. That was a lot of algebra. Okay, so we want to now talk about this binomial coefficient and see what's so interesting about this. Okay, and so in order for us to do this properly, I have to introduce a lemma. Okay, and a lemma, Lindstrom-Gessel-Vienno lemma. And what this basically says is if you have if you have the vertices of a directed acyclic graph, okay, and you have all of your vertices denoted by A and B, these sets A and B, okay, and you construct this matrix where each entry happens to be the product of the edge weights, okay, of each of the paths between A and B. Okay, so A here, so this would be between starting at A1 and ending at AB. And you construct this matrix here. So what the lemma says is that if you compute its determinant, it is actually the sign sum of over all the n tuples of these non-intersecting paths from A to B. And so in our context, these edge weights, it turns out to be precisely the binomial coefficients. So just to remind you again, okay? So if the determinants that we have consist of these, and if you can view these as, you can think of each one as counting all the paths. Let's say, for example, if you want to go from this dot right here to this dot right here, and you want to count, you wish to count all the possible paths that, non-intersecting paths that you can, that starts here and ends here, right? You would think, what would you normally think? You would think it would be, okay, you start here, you end here, so you take the sum lambda plus s plus t, and you choose t. So it would be this binomial coefficient here. T, choose t. Okay, and that's just one possibility. That's just between these two paths. Okay, now if you consider all of them, and you range it over, so you have a lot of different possibilities here, right? So if you consider all of them, then you can construct this matrix that has similar that is similar to this one right here. And then when we take the determinant, now we know exactly what we're counting, and it's because of this lemma. So we're counting precisely all of those. And you can see that reflected in the formula there. It's not obvious, but I think maybe you can see, let's see, is it obvious? Let's see. Lambda plus I plus j. Right. So let's pick an arbitrary point here. So let's say this is lambda plus s plus I minus 1. And let's say over here it's j plus t, I think. Yes. Minus 1. J plus t minus 1. Right. Okay, so let's take a look here. So lambda plus I plus s minus 1, and then that's the starting point, right? This is just some arbitrary I here. And you want to, the ending point is lambda j plus t minus 1. Right. Okay, and then you can count t minus 1. Right. Okay, so that's for some I and some j here. And so that's how you get that formula, the binomial coefficient right there in the determinant. Okay, and then we're iterating all from ij from 1 to n in this case. Okay, so now we know that this counts something. That's my point. Okay, so if we know that it counts something. And so what we're going to show now is all these lattice paths actually has a bijection with something called rhombus tilings. And so you're like, okay, that's not really a rhombus, but fine. And that's okay, this parallelogram. But you can see that we can actually correspond the start points to the length of the edges of this parallelogram, okay? And then we can also do the same thing here. So start points down here, sorry, and the end points up there. Okay, so these would be the start points here, and these would be the end points here. And you're like, okay, but where are the rhombi? In this case, here you have a parallelogram with a triangular grid. Okay, great. Okay, so does everyone know what a rhombus looks like?
It's two triangles.
Yeah, two triangles. Yes, exactly. Okay, so there's actually a lot of possibility here. So you can have two triangles that connect in this manner. You can have two triangles that connect in this manner. This one right here. Okay, and then you can have two triangles that connect in this manner. Okay, and so if you want your rhombi, you just delete the two triangles, and there you have it. Yes. Okay, and so you ask yourself, okay, how many of these rhombi can you place in this parallelogram? Okay, and so in order to correspond this in a one-to-one way, you first look at these start and end points of these paths, okay, and correspond it as one of the triangles. We'll just color it black for the moment, okay, and now remove an appropriate, this is just one possibility, okay, there's a lot of different ways you can do this, right, so, and this is what we're trying to count. So we remove all those triangles, and you get a collection of rhombi, and you can actually see, if you shade according to the three different styles, you can actually see these paths coming into play, and it becomes very obvious how the one-to-one bijection works. And so, right, you can actually see the path. You start here, and then you go up and left, and then you get that, right? So this is just one possibility that you can do. But we want to count all of the possibilities, and that is what our goal is, okay? And so you're thinking, okay, this is kind of a hard problem. How could you count this? There's a lot of different possibilities in terms of where you start the points. You can start at different subsets. You can end at different subsets. You can do a lot of different things, right? It's not so easy to see how to count this, okay? So we're going to try to show a simple example of how we can simplify the counting problem, at least. And so the simplified version of this is when s equals t. So when s equals t, remember that we have that piecewise, for the determinant it was really complicated, and Doran had suggested, oh, that doesn't look so nice. But when s equals t, you have it simplifies very nicely to this determinant where it's just the sum of the principal minors. Okay? And so now we can have an interpretation for this. And we can try to understand how you can count all the possible rhombus tilings. Okay? So for SS, we count all the k-tuples and non-intersecting lattice paths. And keep in mind here, the start and end points are given by the same k subset. So you can have start points 1, 3, 5, so the end points will be also 1, 3, 5, for example, where you start your path. Okay, so just to give a pictorial example, here you have s equals 2, t equals 2, n equals 6, and lambda equals 2. So this is just a specific example here. And the parallelogram looks like this, and so we have 6 possible places to start, 6 possible places to end in this case. Okay, and I don't know if you remember the picture from before, so how the s and t come into play is exactly, so this is the end part, and then the lambda plus s is this length, and t will be this length, the vertical length here. Okay, so the issue, okay, I cheated, sorry. So the issue here is that it's quite complicated to consider all of the possibilities of these subsets that you want to start and end from, right? And so is there a way that instead of considering all of the possibilities, you just have one cohesive way to count all the tilings all at once? And so the strategy here is not due to Christoph and Ake, it's due to Cotton, Teller, and Chigu, I believe, is the one who are the ones who figured out how to count these rhombus tilings in a very simple way. And the way we do it is we take that parallelogram, original parallelogram, and rotate it by 120 degrees twice. Okay, so you get a total of 3 parallelograms. And we have to arrange it in a certain way where we don't have to keep thinking about, oh, when should I remove the triangles? Which paths am I considering? Instead, we allow the rhombus tiling to go over to the other side, so to speak. Okay, so instead of trying to rearrange, instead of trying to just imagine all the different possibilities, you just do it all at once, right? And so, all at once meaning this. So now, the start and end points match, and so now you're allowed to go over to the other side, so to speak. You're allowed to place a rhombus here, okay, match according to this. And I want you to notice that actually there is a space in the middle that is not considered because of the way this is arranged, because we don't have a perfect match in the center here. Okay, so we call this the hole. And that is where the word holey in the title comes from. Okay, so and Christoph does not claim to be the inventor of this word. However, he liked it so much he wanted to put it in the title.
So, Kazantala and I made it up?
Yes.
The word holy?
No, they didn't use the word holy
no,
either.
somebody else.
Yeah. Yes.
But I
so the reduction
independently.
Yes.
No.
Okay, so there's a couple of issues here. Now that you connected everything, there's a possibility that you could lay a rhombus right here in the white area. But we actually don't want that because we have our start points here and our end points there, right? We actually don't want to go over to the other side in this position, okay? So it's best to block it off. So by putting a black line there, we are indicating that we are not allowing the tiling to go over in those places. What else don't we want? We also don't want to overcount either. We want to make sure that we are considering only non-intersecting lattice paths. And so the way we ensure that is to make sure that these, the rhombus tilings are these pictures are cyclically symmetric. Okay, so our rhombus tilings have to be cyclically symmetric in this case. And so that's how we avoid the overcounting as well. Okay, and so if you end up removing the triangles and now we're allowing all the possibilities, we just have to figure out how many ways are there to tile this hexagonal shape with this hole and blocking these places, preventing it from placing a rhombus tiling over those places. And that's what we have to count. And yes, and it's easier because you do less work because you just consider this picture as a whole. Okay, so that's pretty cool, I think. Yes, how am I doing time? Okay, I'm going to speed up now. All right, so just in summary, this determinant counts the following rhombus tilings of a hexagon with a funny shaped hole and that these rhombus tilings are cyclically symmetric. And the whole has the shape of a triangle of size lambda, as you can see, based on the way it's pushed together with these boundary lines of length x, s. Okay, and yes, it's due to Kaitenteller and Jiku, at least for s equals 0. And just to end my part and hand off to Christoph, we have a really simple example of a 2x2 matrix. Okay, so just specifically for s equals t equals 1, and n equals 2, and lambda equals 1, we obtain a total of 20 possible rhombus tilings. And so in Mathematica, you can actually show all 20